The electric drill you see here is a perfect example of how electrical energy gets converted into powerful mechanical work. Let us start from the very beginning where everything begins, the power cord. When you plug the drill into a socket, alternating current flows through the live and neutral wires inside the cord. These wires are usually colored red and green for easy identification. The current remains waiting at the trigger switch until you decide to start the machine. The trigger switch is not just a simple on and off button. In most modern drills, it acts as a variable speed controller. When you press it gently, only a small amount of current passes through. Press it harder and more current flows into the motor. This is how you control the speed of the drill bit without any gears. Once the switch is pressed, current travels to the field coils, also called the stator. The field coils are made of copper wire wrapped around iron cores. When current passes through them, they become strong electromagnets and create a powerful magnetic field inside the drill body. Right in the middle of this magnetic field sits the armature, which is the main rotating part of the motor. The armature also has copper windings and it receives current through two carbon brushes that press against a segmented ring called the commutator. As current enters the armature windings, they also become electromagnets. The magnetic field of the armature tries to align with the field of the stator, but the commutator keeps switching the direction of current at the right moment. This constant push and pull between magnetic fields makes the armature spin at very high speed, often more than 200,000 revolutions per minute. You will notice colorful sparks near the carbon brushes. This is normal and happens because the brushes are transferring current to a spinning commutator. The sparks show that energy is being transferred and the armature is alive with electricity. All the spinning creates heat, so a small cooling fan is attached directly to the back of the armature shaft. As the armature rotates, the fan also spins and pulls cool air through vents in the drill body. The air passes over the hot motor parts and exits through other vents, keeping the temperature under control during heavy use. Now the armature is spinning too fast to directly drive a drill bit. If we connected the bit straight to the armature, it would have high speed but very little twisting force. That is where the gearbox comes in. The gearbox uses a set of gears to trade speed for torque. A small gear on the armature shaft drives a larger gear, and this reduces the speed but multiplies the turning force. This is why your drill can push a screw into hardwood without stalling. The gearbox output connects to the main spindle. The spindle carries the chuck at the very front of the drill. The chuck is the part that holds the drill bit tightly. It has three jaws that close in when you rotate the chuck sleeve. Once the bit is locked, all the torque from the gearbox flows through the spindle into the chuck, and finally into the drill bit. This is the moment where electrical energy has been fully transformed into mechanical energy, ready to drill holes or drag screws. So in summary, current flows from the cord, through the trigger, into the field coils and armature. The magnetic interaction spins the armature at high speed. The cooling fan keeps it safe. The gearbox converts that high speed into strong torque. The spindle and chuck deliver that torque to the bit. Every part works together in a precise sequence, and that is how a simple squeeze of the trigger creates the powerful rotation you need for your work.